Okay, so then we switch from the first to the second point. As I introduced earlier, the difference is that this convex proper function now is no longer an indicator, but more complicated. I'll focus on a specific one for a very good reason, as you shall see soon. At the same time, this specific choice of the non-convex, convex non-differentiable part is sufficiently general. So we already discussed total variation regularization. We already discussed, well, we haven't, but simplified friction was at least on the slide. So what I'm interested in is a functional which has a non-differentiability because of the norm. There is an operator B acting on the object of interest Y. This could be an S could be the domain omega, S could also be just a subset of the closure. For instance, if you think about friction, then you're on the boundary and you may want S to be one part of the boundary, for instance. Alpha is a positive parameter and it's added to a function f, which I assume to be uniformly convex, low semi-continuous with the gradient mapping, which has a certain property here. Okay, so it's a kind of Lipschitz condition, if you wish, on the gradient. So it's kind of strong because it's global. You may consider some local versions, but for the time being, I stick to the global one. Kappa is the corresponding positive constant. Okay. So corresponding to the setup here, I try to be quite general. So which means the output of the operator B, which is supposed to be linear and continuous from our space Y into L2, could be some matrix valued quantity. Okay. So this is obviously meaningful if, for instance, B is like a gradient type mapping, then we have to make specific choices here. But in total variation, for instance, you might be interested in color images. Then you have to imagine that each color channel, RGB, is one component, and then the gradient acting gives rise to a matrix valued quantity. So there is some generality here in this notation as well. And everything should be less or equal to the overall dimension. Okay, so this will be the setup for a while now, and this will be the give rise to variational inequality if we write down first order optimality condition as we did it earlier today. Okay, so how are we going to tackle this problem? I think what at least those people who have worked on continuum mechanic problems have already done occasionally is to look at conjugates or polar functions. This is part of the reason, of course, why I was restricting myself to something like this, but again, at the same time, many interesting problems, as I already mentioned, are covered by this particular choice. Now, I'm interested in the convex conjugate or polar function. I'm sure everybody knows, but I'm just quickly flashing it up to remind us. So the star here denotes this polar, and it's essentially an object which gives us information on the behavior of the slopes of the function f. So you take the supremum over all y in the primal space, so to speak, y, of this function here, where you have p, which is the variable of the conjugate or the dual, y star, minus the convex function f, and this is what you need to compute. Again, in general, we know that computing supremum problems is complicated, even if the function f might be convex. I mean, then at least we know something about existence, possibly, or uniqueness, depending on level of convexity, like uniform or strict convexity. But still, an explicit formulation could be quite cumbersome, but for certain formulations or problems or functions f, we get an explicit form for f star. Now, for instance, if we go back to our model problem here, and let me ignore the operator b for the time being, and just consider alpha times the L2 norm of some quantity z, which is in some L2 space. Then I may compute the conjugate, and if I compute the conjugate here, I get the g star of some quantity q being equal to an indicator function of such a constraint set here. Okay, so if you look at the conjugate of the norm function here, the conjugate is an indicator function of the set f, which is all L2 vector fields or quantities which have a pointwise norm not not greater than alpha, almost everywhere. Okay, so this is observation number 1. So in this particular case, ignoring the operator b, we can get this conjugate. What can we do with this quantity? Okay. So there is this concept of Fenchel or Legendre duality, which I'll bring up here because what my goal is going to be, I'll take this problem which has this non-smooth objective. Of course, you may say, well, we know how to handle non-smooth objectives numerically, so why not just go ahead? Well, sometimes, that's my claim at least, it pays to look at the dual problem because the dual problem may have a structure which is probably already covered by something that you have at hand, solver-wise. And let's see how it's going on in our context. Okay, so what is Fenchel duality? So we assume the following. We have two Banach spaces, capital V, capital Y, and again I denote the dual, the topological duals by star. We have a linear continuous operator, capital lambda, which goes from V to Y. And I'm given two convex functions. Both should be proper. I mentioned earlier what proper means. Both should be lower semi-continuous. And there should exist a point V0 in capital V such that the evaluation of f at this point and g at lambda this point is finite, and the g is continuous at this point. Okay, I think the first, well, these assumptions are kind of course, obviously meaningful because if you look at the minimization problem, as I'm going to do next, we need lower semi-continuity in order to guarantee existence of solutions. For a function being proper, obviously, otherwise it makes limited sense to look at the problem. And this continuity result has something to do with computing this, well, adjoint, but also with respect to looking at what we call here the sum rule for non-smooth functionals. So I was nowhere assuming that f or g are differentiable. They need to be convex, lower semi-continuous, but otherwise they might be non-differentiable. And then, of course, the question arises, how do we correct, well, if there exists a solution, how do we characterize optimality? Well, you write down 0 is an element of the subdifferential of the sum. What you would like to do next, apply a sum rule, saying, well, 0 is an element of the sum of the subdifferentials. Here you have an operator lambda, you would like to apply chain rule, so you would like to have some lambda star subdifferential of g. And for being able to do this, you need certain regularity, and this is what you need, this continuity assumption in order to get this explicit formulation. Otherwise, you just have a very unhandy object, which would be the subdifferential of a sum. This is not what we usually have. Okay, and then Fenchel duality says the following. If we look at the primal problem, where we would like to infimize the sum of f of v plus g of lambda v, then this infimum is the same as the supremum of a problem where I somehow have the convex conjugates or polar functions f star and g star, and the lambda switches to lambda star, but also places from g to f. So this is well established. If you would like to read more on this, there's the, I think, well-known book by Ekeland and Temam on this. There's also, of course, the work by Rockefeller. There's also work by others. But I think an early account is certainly Ekeland and Temam, where a certain special case of dualization, as you can see it here, was considered. Okay, and now you would like to characterize solutions. How can you characterize solutions? Well, we have here this, call it Euler-Lagrange, call it KKD, call it first order conditions, which arise, for instance, if you just compute the derivative. 0 is an element of the subdifferential of f plus lambda star subdifferential of g, and then you just bring in this quantity q and decompose what I just said, and then you'll find out that this is the corresponding first order condition. And this is also there's also another way of looking at it. It links a primal quantity, so the primal solution V bar, to the solution of the dual the dual problem Q bar. So depending, of course, on the operator here and on the functions there, sometimes it might be easier to solve the dual problem, get the Q bar, and compute from Q bar a V bar by solving this system or one of the two equations. Okay. So this is Fenchel duality.
Is there any other relationship between V bar and Q bar?
Any other?
Any other relationship between V bar? This is just these two.
That's yeah. So I would not be aware of any other. And it arises no further relationship, and this one arises just by first order optimality. So if you take this, I mean, you can quickly write it down. So if we so we have this objective, which was f of u, I guess, plus or v g lambda u, and you wanted to compute the infimum. First order condition would be 0, an element of the subdifferential of the sum, which you then decompose into the subdifferential of this one plus lambda star subdifferential of g at lambda u. And then I would need to see how it's done here. Let me see. So we're saying lambda star. Okay. Now we're saying there is an element minus, did call it q bar, minus q bar in this set.
Yeah, and I guess that's the theorem. Is this? There's a theorem which is this equation, I guess.
And that's the first order optimality condition. So you minimize an objective function in u.
The theorem is about the differential of f plus g lambda u is equal to the sum.
Yeah, that's subdifferential calculus. For this, we needed these conditions on the g, that there's a point of continuity, so that we could somehow decompose it in that way. And now you may say, well, if 0 is in there at the solution, which we call bar, to be consistent, then there is an element q bar in that set, which makes it equal 0, and this gives you these two conditions.
Once you've got that equation, I guess that's right.
And these are all conditions which link q bar and q bar. Okay, now let's move on. Now, variation inequalities of the second kind, how do they fit into this framework now? Okay, so let's assume our set V is L2 according to our problem setup earlier. Fenchel duality says, well, now bring in the operator B, now lambda is equal B, and instead of infimizing or minimizing the primal problem, I may maximize or compute the supremum of this dual problem here, and I'm more or less just mimicking what we have seen in the theorem, and now I will have a look at this dual problem. So we already found out that the adjoint, the dual or polar function g star of the g, remember this was just a norm functional, is this indicator. This is why you see here an explicit constraint, so you may either view this as the indicator function for all elements which satisfy a point almost everywhere sense this condition here. So I may as well write it as an explicit constraint. And otherwise you see the adjoint of this functional here, and I use a minimization. I mean, up front we should write here infimize because we might not be aware of existence of a solution. But let's assume there exists a solution, then the minimize is substantiated in a sense, and then we have the minimization problem. Okay. And this is just a relation now. In our setup, remember the f was supposed to be a smooth functional, so I can write down the f prime, and this one is supposed to be non-smooth. It's the subdifferential of this norm functional. This is now the relation between the solution y bar of the variation inequality of the second kind, which arises as a first order condition of the minimization problem, and this solution of the dual. Okay. So in some sense you may say, if you look at the structure now, the non-differentiability is gone because the f star turns out to be differentiable as well. So this is a structural property of the polar function here. But the non-differentiability somehow is now hidden in this inequality constraint. But of course, if we think back of what we did before lunch, you may say, well, depending on the f star, but we are now looking at a similar setup, because now here we have an indicator function of a convex a set, even bounded and closed, of course, non-empty as well. So we have a setup which is very much related to what we had earlier. Okay, so now let's be even a bit more explicit concerning these first order conditions. Now the first order conditions look like this, really. So we have here this derivative of this functional here. There is a Lagrangian multiplier associated with these constraints that the p bar should be less or equal alpha almost everywhere. And this q is a derivative of this norm functional. So at every point x, whenever the norm of p bar at x is not 0, I get this object here from differentiating the L2 norm. Whenever I'm at the situation where p bar at x equals 0, well then, because of the kink at this point, I get a set-valued derivative, and it turns out for the L2 norm, we just get the unit ball, the closed unit ball in the underlying space here, and this would be the corresponding set-valued component here. So I need to find such an element q bar satisfying this equation. And the multiplier has to be in a certain complementarity relation to the inequality constraint, which you can see here again using this max or plus notation as we've done it earlier. This is equivalent to p bar being less or equal alpha, lambda s being greater equal 0, and the product of this one with that one vanishing. Okay. This is what I have just said. So this is the usual complementarity relation. So this is now really the nonlinear first order system. And this in here gives rise to usually some sort of partial differential equation here, depending on the involved functions and operators. Okay. Now, well, let's just do what we did earlier. So we say we have a variational inequality of the first kind, characterizing first order optimality of this dual problem. So we may just go the same path, which we did.
Mind what alpha is? Sorry.
Well, alpha is just this, I may have left it out. It's just a sort of weight in front of the non-differentiable term.
So a simple example of this would, you could just, f could just be the,
well, let's assume
the Dirichlet norm squared, and the second term could be, y could be a scalar, and it could just be the modulus of y.
Could be, yeah.
That would be the simple thing.
Would be a simple one.
And then you're saying you can relate that to an obstacle problem.
Yes.
And B is the, and you can take B to the identity.
For instance, yeah, for instance.
And so you're saying that minimizing the Dirichlet energy plus the integral of the modulus can be related in the graduality to an obstacle problem.
Yes.
Mod, yeah.
Mm-hmm. Yeah. Which I claim is very often easier to solve. Okay, so now. Okay, so let's do what we did before lunch. We would say, okay, we take the indicator function of that set. We take its Moreau-Yoshida regularization. I'm leaving out the lambda bar. You know that I could also bring in the lambda bar in order to be more general, but I just would like to simplify the discussion at this point. Ignore the red term for the time being. Then this would look like what we have seen earlier. Okay. So it turns out for the obstacle problem, this is already enough. So if this were the energy which we had this morning, and for instance, this would give rise to the Dirichlet integral, as it was just mentioned, then we would end up with the problem where I said that we can set up a semi-smooth Newton method and everything is fine. Well, it turns out that in general, if I'm that general as I've displayed here, things are a bit more complicated. This is why I'm adding this term here as well. I mean, I also use a parameter gamma. Remember, gamma has to go to infinity. So this makes this term vanishing as gamma goes to infinity. I could use a different parameter, but the idea is the same. And I'm adding here a squared norm with an operator C. And the operator C should have this kind of property. So in a sense, it says, unless you have the 0, it should not map a non-zero object onto the 0 in a sense. So there's a kind of regularity in this operator C here. Particular example you may have in mind, for instance, is C being the gradient and H being some H01 space, for instance, so that you can apply vertex inequality, for instance. Okay, and the regularization is necessary whenever it turns out that the p bar is not in L2 plus epsilon. So this is a bit of a mystery maybe at this point in time. I'll come back to this. And it has something to do with differentiation, generalized differentiation of the derivative of this term here. So that the derivative will involve the max, and we will need to understand in what sense this max admits a specific generalized derivative which is suitable for our purposes of proving locally superlinear convergence of units.
That term is just for regularization.
Is for additional regularization. You need it sometimes, you may not need it always. In particular, you don't need it whenever you can already show that the solution regularity gives you a p bar which is in some L2 plus epsilon, so as small as you wish, but positive. Okay. If that's the case that you're in here, you dismiss the term, otherwise you will keep. Okay, well, first order optimality is a routine work. You just write it down. You end up with this condition here. And the lambda bar, as before, is the derivative of this term, not lambda bar, sorry, lambda gamma. And it acts as a kind of, let's say, approximation of the true multiplier, if you wish. And this obviously gives us some additional regularity so that we get it.
It's like some viscosity term, epsilon.
For instance. So, I mean, if we stick to my example that C is the gradient, and this would be, for instance, the negative Laplacian with 1 over gamma. Now, if gamma is very large, it's like, as you're saying, it's a sort of viscosity term giving us some regularity so that we fit into that framework. Okay. And the Q gamma, again, looks a bit complicated, but it is just the derivative of the norm function here. And it's the same thing. Unless we hit the 0, we have this quotient here, and if we hit the 0, it's set value. So this is now the system we have to solve. So there is a partial differential operator usually emerging from this here. There's a partial differential operator very often sitting in there. And this gives rise to this kind of non-smooth, non-linear PDE which needs to be analyzed and solved. Okay, now let's be a bit more specific in order to make things more visible, so to speak, and more explicit. Now let's assume the adjoint F star is of such a nature. So we have a bilinear form which is continuous and coercive from y star cross y star to r. Z could be some sort of shift in y star, and B is just a real. Okay, what would be examples? I think we already discussed the Dirichlet energy. If we discuss the Dirichlet energy and you take its dual, then it would be an example which fits in there, so this quadratic. But there are others as well, as we shall see later. For instance, if we look at the energy associated with the simplified friction problem, it will fit here. If we look at the energy associated with Bingham fluids, it will fit here. And if you look at the energy associated with some regularized total variation term, it turns out to fit into this framework as well. So we cover continuum mechanics, image processing, and other fields with this assumption. So it's by no means extremely limiting, but of course we may think about other terms as well. Okay, well, the first observation is, again, as before, what do we get if gamma goes to infinity? And we understand that if gamma goes to infinity, then, well, I think you should ignore this gamma late great equal gamma bar, in the sense that we only need to be positive, otherwise we have maybe some difficulties, but because of the 1 over terms. But otherwise we just get again that the dual solution converges in this sense here. So we have the B star acting on this dual solution P gamma, and it converges to the B star of the dual solution of the original dual problem without the regularization. So this is a kind of consistency consideration, still valid as before for variational inequalities of the first kind. And now we have to be a bit more technical. And again, I think feel free to interrupt in case there are too many spaces around, but the idea is the following. So in contrast to the variational inequality of the first kind before lunch, we have now a more general setup. And for some of the problems, we need additional regularization so that we can get a certain norm gap, which is going to show up soon in the Newton context. And this gives rise to this complicated introduction of additional spaces here. So remember H, I'll just go quickly back. H was the space which I introduced here in connection with this operator C, and a particular example could be if it fits to Dirichlet energy with H being H01. So then we have the following assumption, one of the two cases. Either we have that H hat equals H, which is embedded into LR for R larger than 2 in a certain setup. Remember, we have this operator B with images at every point in RL cross M, and if L plus M are 2, then this is one assumption. Or we are in a situation that C star C as a mapping from H hat to L2 is a homeomorphism, and H hat embeds into H, with H hat being also embedded into L infinity. This can be weakened as it turns out, but I think the discussion would be complicated. I'll come back to this a little bit later, but what we need here is essentially, and if we write down first order optimality, C star C emerges, and we would like to have some sort of regularization of viscosity term, as it was mentioned earlier. This is why we need that C star C has good properties, as written down here. And we need that H hat embeds into L infinity, as at some point, if you, and I go back again, if you differentiate this term, it gives rise to something which looks like this. Now in our first order system, remember before lunch we used this system, which we would then feed into the Newton solver, and now we need to apply the Newton solver. So which means we need to understand the generalized differentiability of this term, which looks complicated because there is a non-smooth object in here, so there is a norm. The norm sits inside another non-smooth object, which is the pointwise max of 0, whatever is in here. And this is multiplied with an object Q, which either is a quotient, again with a non-differentiable quantity, or comes out of some set-valued object. So we need to differentiate this. Well, first observation. We never really suffer from the set-valuedness because alpha is supposed to be positive. So whenever the P of gamma at some x is 0, well then this max already makes it 0, and whatever the Q would be chosen out of this unit ball, it doesn't matter because we already get the 0 from there. Okay? So which means the only interesting case is whenever we are here, and but still we need to understand in what sense we can differentiate in a generalized sense this complicated product. And for this differentiation, we need, for the time being, this embedding into L infinity, okay, of H hat, because I can then understand P gamma as being an element of H hat. H hat embeds into L infinity, which means, if I go back, which means small perturbations of P gamma. Let's assume P gamma is strictly below alpha. And if you take a small perturbation of that P gamma, then the L infinity topology works. And if the perturbation is small enough, you still stay below alpha. That's important. If you don't have L infinity, you need to have a sufficiently large norm gap, which complicates a bit, but this is why I don't touch it here, but could be done. But in general, if you don't have, if you just have some LP, or L, let's say LR space, R less than infinity, then the trouble, of course, is the usual one. You shake a little bit in LR, and you could immediately violate a point was almost everywhere constrained on a set of positive measure. And this is problematic here. Okay? This is why we need to go into the L infinity topology, because then we can guarantee that we stay within. Okay? Otherwise, we run into this difficulty. Okay, so this is the reason for this second assumption. And again, this is a question of choice. It's not entirely limiting, and usually this embedding, for instance, can be thought to come along if you have a regular solution of a variational inequality being, for instance, in H2 and dimension being less equal to 3. Okay, as I just said, for the application of Newton's method now, or the generalized version, we need to understand whether this quantity, and I use now this Q of P for this quotient or this set valued object here, as we discussed it already several times. So we need to understand whether this object here can be differentiated in a sense useful for Newton's method. Okay. This is the product here. Okay, well, before I can do so, I think I should tell you a little bit more about Newton's method. So I leave the context for a second and go into a very general Newton slide. So we have seen Newton's generalized version of Newton's method earlier in function space, but I haven't really explained much about it. I just wanted to focus on the regularization, the fact that there is a solver, the fact that we need to study sensitivity with respect to gamma in order to find a path following method, and so on. I think now it's the time to speak a little bit more about Newton's method. Well, let's assume we are given the following. We have a mapping G, little g, from some Banach space capital X into a Banach space capital Y. Okay. Well, first of all, we know that in certain situations we can generalize the differentiability concept. For instance, there's the book by Frank Clark, so there's a very wide analysis on generalization of differentiation to convex but also local Lipschitz functions in general settings, also in finite dimensions. There's of course also work by Rockefeller and others. But just having a generalized derivative turns out not to be enough for the purpose of Newton's method. First of all, you may not be able to guarantee convergence, and even if you're able to guarantee convergence, it might only be linear. So we need a bit more regularity of the function, and this is what I'm bringing up here. So I call this mapping G now in a neighborhood U in X, Newton differentiable in this neighborhood U, which is supposed to be open. If there exists a family of mappings capital G from this neighborhood into the continuous linear operators from X to Y, such that this approximation property holds true. Okay? So G of X plus delta X minus G of X minus capital G of X plus delta X in the Y norm equals little o of norm delta X in X as delta X goes to 0. Quick look may say, well, what's the difference to Fréchet differentiability? Well, there is a difference, because for Fréchet differentiability, you would never evaluate the candidate for the derivative at the sort of perturbed point. You would always evaluate it at your point of interest. And if you look at this and, for instance, take the max of 0 and something operation, then you will find, let's say you start in finite dimensions, you will find it satisfies this limiting behavior here. Okay? So there are examples of non-differentiable objects which have such a limiting behavior, and the one that I just mentioned from Rn to Rn, say with a pointwise, a component-wise max, would be just one example, but there are many others. Okay, and I call such a G a Newton derivative or a Newton map. Now, the same is with Newton method, which arises once I have such a derivative, is the usual one, I would say, pattern-wise. It looks like a classical Newton's method. What we do is, we would like to find a solution X star of G of X star equals, so such a G of X star equals 0. You start with some initial guess X0, and then you just iterate as you would expect it. So this is a sort of generalized linearization of G at Xk, and you would like to find its root. But remember, the capital G of Xk here is a Newton map, and since I already brought this example of the max, we should not believe that the Newton map is always uniquely defined. So it could be set valued, obviously. And then, of course, you have to make a choice. Okay? And then the result is the following. Assuming that there is a solution, and assuming that in a neighborhood around this solution, X star, the G's which I pick are uniformly invertible, and I'm starting sufficiently close to the solution, then I get the Q superlinear convergence, which means if I take the quotient of xk plus 1 minus x star and over xk minus x star, then this quotient goes to 0 in the x node. Okay, so I have superlinear convergence locally only, of course. But that the fact that it's only local is not a surprise, because also the classical Newton's method would only converge fast locally. Sometimes we can get more than superlinear convergence, even in the non-differentiable case, but in the general setting as displayed here, we should not hope for more. And without this property, I think there is no way to get superlinearity. Okay. So this is now a short introduction to what I call a semi-smooth Newton method, and this is general here because I'm operating Banach space that could be finite or infinite dimensions.
In one you have or a square, then you will get the second.
Here? Yeah, of course. If here I have capital O of norm squared, I get quadratic. So if that approximation quality here changes, well, I get different types of convergence. But this is a sort of smallest denominator in a sense. This is what we at least need to have. And again, for instance, from Rn to Rn, my max example would give you a better approximation. So then you may conclude more than what I do here, but in the general, that's what you do. Okay, now the question is, yes?
Sorry, if we just go back to the last slide. Can you get an estimate for how small sufficiently small is on the x naught minus x star?
I wished, no. I mean, but it doesn't mean it's not possible.
Yeah.
It's just, the point is, if you look into the smooth world, what you would have usually is a sort of inverse of the curvature.
Yeah, it's a
somehow.
Cantorovich, right?
Yes.
Yeah, I'm just wondering if you could do something similar here.
This is a bit more complicated. I'm not aware of this. So I mean, getting an estimate of the radius of local convergence would be quite handy, not just for this purpose, but also for what we discussed before lunch, because we had this inexact solution concept. And again, it would be quite useful to know what would be the radius of fast convergence, because this could give us an idea on how to update and how much we need to, how many iterations we need to. So I don't have this for the time being, and it's a bit more complicated because Newton-Kantorowicz relies a lot on the fact that there is some smoothness and bound on the rate and on the derivatives. In there are generalized versions, but the ones that I'm aware of, well, first of all, they have finite dimensions, and they have a lot to do with norms of the derivative. If you wish, generalized derivatives, if you wish, they have a relation to the width of the subdifferential, and so on. So it's a bit more complicated, and I think, yeah, that's all I can say for the time being. Okay, little excursion, because the question now might be, well, I'm doing all of this in an abstract sense. Of course, being a mathematician, this is a good thing probably to do, but at the same time, I would like to solve a problem finally. So why is it useful to have a certain angle like I do have here on Newton's method? And as I announced in the morning, it's all on mesh independence. And let me explain a little bit of mesh independence just in a few minutes in the context of PD constraint optimization, which ultimately I could again write as a variational inequality in order to fit into the topic here. Okay, so what about mesh independence and Newton's method? Now let's assume, we just had this little discussion after the first presentation that some are also interested in optimal control of PDs. There would be just one example here. So we're doing the following. We are minimizing an objective functional, and this is a very common objective. It's a tracking type objective, but you could conceive other ones. So some engineer or some measurement or whatever gives you a desired state YD, which is an L2, which you would like to track, but since it's a sort of guess, and you have to also pay some price alpha for a control action, which is in average in L2 here. So you have this quadratic fit here, subject to a governing system which describes your physics, so it's very abstract here. So there's a partial differential equation hidden in this operator E with the state Y and the control U, which could either impact in the domain, which is the case that I'm flashing up here, but it could also be U acting just on the boundary in various ways, Dirichlet or Neumann. And let's assume, for simplicity again, the control is bounded by some upper bound B almost everywhere in the domain omega, where you need to solve the PDE. There could be a lower bound, there could be other type of constraint, it could be just a convex constraint, but let's just be explicit and simple and look at this. Okay, so there's one example. I think this is still not very illuminating here, but replace E by the negative Laplacian, replace E by some other second order elliptic operator, could be a semilinear operator, could be anything. Could be also parabolic, so we did it also for Navier-Stokes and other kinds of problems. But in the simplest version, you may think of minus Laplace y equals U and U less equal B. Okay, and this would be the minimization. Okay, first thing, let's assume given U, we get a locally or ideally globally unique Y. Okay, so for the Poisson equation, it's obviously true. If I have minus Laplace y equals U, I get the unique Y of U, which I can then plug in, and I can reduce the problem to a problem in the control variable U only. In control, this is interesting also in situations where, for instance, the control only acts on the boundary, because in a sense you're somewhat reducing the size of the optimization problem, although we should not forget that the solution of the PDE still sits in here. Okay. But at least this reduction step allows me to look at this problem as minimizing an objective, which I call now J hat, subject to a constraint which is usable, which I assume to be in this simple one, but in general let's assume it's non-convex enclosed. Now we are back again in a setup which reminds us a lot of what we've seen before lunch, because if J hat would be now the energy we have seen there, this would be another instance of the obstacle problem, but of course it's here a PD constraint optimization, so there's a different structure hidden in here. But at least the point of view is similar. Minimize a smooth objective subject to a constraint. First order condition gives rise to variational inequality of the first kind.
So the simplest problem being then the E is actually the equation is minus Laplace y equals u.
Yes.
And then what you've got is an obstacle problem which the energy is non-local. It's a
Yes.
quadratic functional. And the
Yes.
smoothest
Yeah.
part of the energy is the L2 normal view.
Yeah.
Because the other one is like an H minus 1 normal view.
Yes.
But otherwise, it's very similar to what you were doing in the
No.
obstacle problem.
That's true, but it would indeed be non-local because of the solution process. Okay, and here it is. So I've written down the first order optimality condition, which is a variational inequality, and it turns out it's a variational inequality of the first kind. So well, of course we have to clarify existence, but for this particular problem it's just Dirac method of the calculus of variations, and the first order condition because of differentiability of the J hat is fine. Of course we need to know a bit about the dependence of y on u, but in the simple example where there's a linear operator, the differentiability is obvious. If it's more complicated, the PDE, then you have to analyze whether y is differentiable as a function of u. Okay. And assuming so, you can differentiate the objective as I did here, and you get the specific format of the first order condition. I'm just bringing this up for completeness purposes. Now we would like to get rid of this quantity here, because obviously we usually do not want to compute the sensitivities of the PD solution. This would be an immense task to compute it. Usually what we do is we bring up an adjoint state.
By the way, you've got an issue, isn't it? Sorry,
Yeah.
people haven't seen this before. There's an issue, isn't there, whether if you're going to consider a semi-linear problem or a
Yeah.
non-linear equation, and it may be that equation doesn't have a unique solution.
Yes.
So your reduced problem doesn't make sense in that. Well, you'd have to work hard to make
Yes.
sense of it.
Yes, I agree, and this is why I stated it. I would need there's a sort of assumption, but if there is no uniqueness, then it's complex. So then it's really an issue. Okay, now how can we get rid of this? So there's a sort of adjoint calculus, and I don't go through the details how it arises. I'll be happy to discuss this later on one of the boards in the house here. But there is an adjoint equation, so you differentiate the PDE operator. So I'm sticking here to this format which I gave you over there. So this may still be a semi-linear operator here. So what you do is you differentiate, you take its adjoint, and this again gives you a partial differential operator linearized at y of u, and you get an adjoint state P which solves this PDE here. Okay. And then the derivative of this reduced objective can be written as P of u plus alpha u. The alpha u comes from the obvious term, which is the quadratic cost term, and the P of u now comes from replacing this y prime by solving the adjoint. So this is a sort of standard procedure, kind of well-known in PD constraint optimization. But the nice thing is now we have this format of the derivative. And now we have to also think a little bit about regularity. Well, let's assume we are in this setup again here. U is an L2. Okay, the derivative is an L2 upon identification with its dual. This is already clear from this term here. Now there's the P of u. Now how do we get to the P of u? Well, first we solve given u a PDE. Now let's go to our simple example of Poisson's equation. Let's assume u is an L2 if the domain, well, at least we have y in H1, H01 for instance. Okay. Now if the data yd here is an L2 only, and we look at the adjoint, this is the derivative with respect to y, we again have an L2 right-hand side of a PDE, which in our simple case again is minus Laplace of P, so P is still in H1. but sometimes you may even have a higher regularity gain by smooth domains, data regularity, and so on. But it's always safe to assume here in this particular setup that the P of U is more regular than the U, because it solves at least the PDE, or maybe there are already two PDE solves in between, if you count both. So this gives rise to the following structural assumption, and this is quite common in this setup. You would say, well, I can write this, mapping operator here as an operator A of U plus alpha U. I consider the A here a smooth mapping, and again this was the case in our setup because Y was supposed to be differentiable with respect to U. This is a linear equation, so the P is differentiable with respect to U. As a continuous differential differentiable from L2 to L2, well, this sounds fine. This sounds even relaxed. But then I would like to have a local Lipschitz property from L2 to some Ls s larger than 2. Well, is this a lot to ask for? Not really in this context. For some applications, yes. But here, if we solve again, let's stick to our simple example, Poisson's equation minus Laplace P equals this L2's right-hand side. Well, the solution is in H1. Now, if we're in H1, that we know that regardless of the dimension, we're always embedding into L2 plus a little bit. The little bit is larger, of course, the smaller the dimension is, but we'll always be in some L2 plus epsilon, and let's call this L2 plus epsilon s, Ls. So this is a structural assumption. Okay. Again, what I do next is I bring in a Lagrangian multiplier, but by now I think you know how to do this. So instead of writing the variational inequality, you see again a multiplier lambda, which has to satisfy these complementarity relations with respect to the inequality constraints. And again, I replace these relations by this non-smooth equation, as we have done it already, and I end up with a non-smooth system as we did it before lunch. So in this context, PD constraint optimization fits into this framework, which we have seen earlier, and you may, of course, use the earlier method. Although my claim is, for this particular problem, I would not advise you to use the Mori-Yoshida regularization because it already works the way how it is. And this is more or less the point of this little excursion. So we can further reduce the problem in the following way. We may say, okay, we know how lambda looks like, this equation. So we express lambda in terms of U, bring it in here and there, and choose C equals alpha. Remember, C has to be positive, but otherwise there's no demand. We can choose it as we wish, and alpha is positive anywhere. And if we do so, the term inside the max simplifies and looks like that. Okay, because here we have alpha U. From here we get minus alpha U, so the alpha U is gone, and otherwise just the A of U stands there. Okay. So now what we end up now with is a non-smooth operator equation. Again, remember the A of U means solve the PDE, solve the adjoint PDE, and evaluate. So this is what this does. Okay, so there are two PDE solves involved. But this is now the non-smooth operator equation, which we need to solve for U in order to solve the problem. And since it was a convex problem, it's a convex problem, if we solve the first order condition, it's also sufficient for getting a solution. So solving this really gives us a solution, which is, of course, in general not the case. So now if we go back, we have now this G of X being this particular mapping here. Okay. Now, first we need to understand, is the max operation, so now we have here max of something and 0, is it Newton differentiable, if you would like to apply Newton's calculus? And of course, the spaces are obvious, because we map here from L2, so U is an L2, remember, and the image space is L2. Okay. So, well, it turns out, well, of course, we should not be surprised that differentiability in general spaces is always related to some norm gaps. But the max, of course, it's nonlinear, it has a kick, but at the same time, it looks, I think, probably more innocent than it is. We have the following observation. If we consider the max as a mapping from LR to LS with R equals S, it's not generalized differentiable in the sense as I've displayed it before. Okay, it's not. It is, however, if we would replace these infinite dimensional spaces here by Rn. If we map it from Rn to Rn, well, of course, there is not such norm issue here, but then it satisfies such a Newton mapping property. So there is something, of course, profound, which comes again through infinite dimensions, and we know that if there's a norm gap, like R is larger than S, then the max has this property.
Can you just go back to set?
Yeah.
Previous slide. So where is the one has got this one of the sorry, which one's R is S R is S is equal to 2 and R is bigger than 2, is that? Or is it the way around?
Let me just go back. Yes, in our setup, we need to find a situation where I have an interpretation where, well, S would be 2, because that's my output space,
R is less.
and R should be larger than 2.
R is bigger. So if we go back then, so where is the R and where is the...
So that's the max. Now the S would be the image space of the max, and the image space is L2, no matter what, because, well, in this situation, this is certainly natural, because our gradient or derivative of J would be in L2, and we should expect that this here holds in L2. Now the question is, and then of course the U starts in L2. So it looks a bit hopeless, because we just had this result saying if R equals S, we are done. There is no, in a negative sense, done. We cannot have this Newton differentiability result. But then we should look at the structure here, and this is why I was emphasizing these PD solves all the time, because inside here we have this A operator, and the A, at least, remember, relates to solving the adjoint. So there's a PD solve. And if the solution in our little example is in H1, then this object, and assuming B is smooth enough, can be in LR, R larger than 2. Okay? So although I start with...
So you're saying that the alpha x is cost differentiable, and that's going to be in L2. But
Yeah.
the A of x is smoother, so
It's
then
smoother.
you can differentiate
Yes.
that term using, so that's...
Yeah.
So it's this, that's the...
So the idea is, so the setup is the reduction step allows me to find inside the max a mapping which has a more regular output space,
That's the observation.
and that's the observation. And because of that, although I start in L2, I have a more regular player in here, and although the image space in L2, this regularity prevails in a sense and allows me to conclude Newton differentiability. Okay. And this is also the reason, and if you go now through this calculus for the obstacle problem, in the smooth case, you will see it doesn't work for the obstacle problem, because then the A would really be the negative Laplacian.
Yeah.
And there is no regularity. And this is why we needed to go through this path following step. But if there's a regularity gain, as it's going to be here, avoid path following, because the method operates already fine the way how, for the problem how it's set up here. Okay. All right. And that's the observation. And in our context, well, it turns out that we have this smoothing property as we just discussed, and we have this local convergence result for Newton's method. See what happens. Little test case. This is the well-known simplification of the nonlinearity coming from the Ginzburg-Landau model. We have a bilateral constraint on U, otherwise it's a semi-linear elliptic equation where the control acts on the right-hand side. It's a bit academic, but nevertheless, I think I just want to demonstrate the behavior of the algorithm. We have certain data here. We look at residuals. Well, first of all, we look at the quotient here, which is the one which that I mentioned is important to study superlinear convergence. If this quotient goes to 0, we have superlinear convergence. This could be used for linear convergence, and this is more or less the residuum of the first order equation. So don't get worried about the details here, but this is just the first order system which we have seen before in a reduced form. Okay, so there's an optimal state, there's an optimal control, and you can there's an optimal control and an optimal state. You can see an activity of the control on the upper bound, you can see an activity on the lower bound, and here is some figures. So H is again the meshed width in 2D, uniform in each direction. This is how the residual behaves, and you can see that after 4 steps, we already have quite a small residual here. And this is more or less regardless in each line the same somehow. Let's just look at the lower table here, the quotient for superlinear convergence. Well, we can see that this quotient nicely goes to 0 as we look at the different meshes. But of course,
how was the formula of the Q again?
Second?
To a slide.
The Q. The Q was just the quotient. So you have a solution U star, and you try to understand how well UK approximates U star compared to UK minus 1. And if this quotient goes to 0, then you're approaching the solution faster than linear, superlinear.
How you calculate? Oh, can you calculate?
Well, the U star, of course, there's the usual thing, you calculate it up front. We don't have an explicit solution, we calculate it up front on a fine mesh, which we then restrict back to the mesh which we consider here. Okay, and then we should not only focus on the lines, but also on the columns, because the columns tell us something about how the method behaves under mesh refinement. Because after all, I was saying we would like to have mesh independence. And as you can see, these numbers quite nicely stabilize as you refine the meshes. So there is indeed a belief that there is a mesh-independent convergence behavior. Remember, before lunch, I showed you this Newton's method for this finite dimensional one for the obstacle problem, where the number of iterations was almost doubling if I halved the mesh size. Now I'm halving, but the numbers stay stable. This is a strong indication that there is mesh independence. And indeed, mesh independence can be made explicit, or rigorous, I should rather say, under assumptions. So let's assume that the set where U equals B and the J hat plays the role of the Lagrangian multiplier, and the multiplier are 0 simultaneously. This would be the set where we have so-called lack of strict complementarity, has measure 0. So which means if we go back to the max terms, the non-differentiability happens only on a set of measure 0. Let's assume our discrete solution approaches the continuous solution. This is a requirement of with respect to discretization. Let's assume the same is true here for these operators. Remember, the A was this forward solve, adjoint solve, and if we say that as the mesh size goes to 0, we should have these operators approach this operator, and it's just a question of discretization here. Okay? So we should have a certain consistent discretization, and please pay attention, we need to have this property here in LS, which was the output space for our operator equation. Okay, then we have what I call here a locally uniform Lipschitz property, which means essentially the following. This operator A should be locally Lipschitz from L2 to LS, with a certain Lipschitz constant. And there's a certain locality radius delta naught. And then local uniform means that there is also a mesh width h naught, such that for that mesh and all finer meshes, you can use the same local radius and the same local Lipschitz constant for the discrete process and the discrete operator. Okay. Again, you can. This is a requirement on discretization. You can check that certain discretizations, for instance, for a simple discussion problem, would satisfy such a property. In particular, if the PDEs are linear, it's just a question of regularity and not so much of local Lipschitz. It's all satisfied. And finally, we need what I call a uniform linear approximation property. What does this mean? Well, remember the operator A was supposed to be continuously differentiable from L2 to L2. Now I assume that, well, if I look at the linearization in a little neighborhood of radius delta naught around U star, well, I have a certain function rho which goes to 0 faster than its argument goes to 0. So this is what we would usually see for differentiability. And I should be able to use the same function rho for the discrete process, okay? Once the meshes are fine enough, okay? So this is a kind of linearization property which we have anyway because of our regularity, but we should be able to have the same remainder function, so to speak, for the continuous as well as for the discrete process. And again, it's a question of error estimates on, for instance, for a little discussion problem, this would be satisfied. Because then the following result holds true. So we have our G from L2 to L2. This was just what we had earlier with this embedded smoothing property. Then in S, and we assume that the Newton maps which we select, so the S and SH, you should consider these as selectors. Because the question is, if the derivative is set valued, well, am I allowed to take any of those, which means I'm at the point UK, and I just feed an oracle and say, oracle, here I give you UK, please return me a generalized derivative. Well, the answer is yes, this is fine, but But sometimes, for instance, for the max function, you may not consult an oracle, but make your own decision and say, okay, well, I can compute the derivative, and the derivative of the max function is, for instance, a characteristic function. That would be a Newton derivative at this point. And then you have a specific selector S here. So if for all elements G which you select, doesn't mean for the whole subdifferential or generalized derivative, you have this boundedness, uniform boundedness of these Newton maps, inverse of the Newton maps, in a neighborhood of the solution. This is what this means here with this radii, delta 2 and delta 2 prime. Then the result is the following. You can give me any radius or any rate of linear convergence you wish to see. So you give me a theta between 0 and 1. Then I can say, well, there exists for each such theta a radius delta bar and a math which h bar, such that the continuous as well as the finite dimensional discrete process converge at the same linear rate. Okay, for meshes which are sufficiently fine, and for starting points which are sufficiently close to the continuous and the discrete solution. So this would be a typical mesh independence result. Okay. So both processes converge at the same rate. Okay. And this could even be improved if you wish, but I think this is the essence here. And this is probably one of the main reasons why we're going through this Banach space consideration for numerical methods, because ultimately one can prove such results. Okay. All right, so then let's end the excursion here and let's return. Variational inequalities
might be ending now. We're going to 4 o'clock.
That's what I thought.
Yeah.
I mean, I may end here, so it's up to you. I mean,
No, you go on as much as long as you want.
No, well,
I was
I was under the impression we were going till 4.
Huh?
I was under the impression we were going till 4, so I'm good for another half hour. So.
okay, so then I'm fine.
How many slides?
Well, how many slides? I think so. I'll finish after this one. So this, how many slides? I don't know now. I mean, I can count them if you want. Maybe 10 or something. Okay. Let's see. 1, 2. Yeah, here we go.
Okay.
And then
Okay.
Fine. So okay. So we ended our excursion. So now okay. So let me at least summarize after this little relaxation. Okay, so before lunch we did this path following for variational inequalities of the first kind. And the reason for path following was we cannot get this Newton differentiability going in function space. I didn't tell you why back then, but now I told you why I would like to have this property, because if I have this property, I can set up a Newton's method in function space, or in this setting even more general in some Banach space, and I can get results like this mesh independence result, and this is good to know because now as you refine your meshes, of course every iteration becomes more expensive, but the number of iterations doesn't grow, or the rate of convergence doesn't deteriorate, so this is good to know. But sometimes, as my little example for PE constraint optimization should have convinced you, sometimes I do not advise you to automatically resort to Morio-Shito regularization, because the problem as such may have inherent smoothing, so that if you go through some reduction step, you already see that there is Newton differentiability. Then don't do anything in addition, because then you bring in a parameter which you don't need, because the theory already works. But for the obstacle problem, it does not, and this is why we needed to go through all of this. Message for variational inequalities of the second kind so far. If there's a certain structure in the objective which gives rise to the variational inequality of the second kind in a minimization context, well, you may consider a dualization, because the dual problem looks like a variational inequality of the first kind, and then again, you either check whether semi-smooth Newton theory works right away. It does sometimes. And if not, well, I gave you one option how to solve the problem by using Morio-Shito. And now, talking about Morio-Shito, for every fixed parameter gamma, the mesh independence theory works. So for every parameter, we have a semi-smooth Newton method which converges mesh independently in function space. Okay, now we get back. Okay, so first of all, remember we had this complicated term from differentiating this regularization quantity here, which was this max of the constraint subject to the derivative. And it turns out it is Newton differentiable. This is quite some proof, which I cannot display here, as a mapping from L infinity to Ls. And the L infinity, I gave you the idea already, is because if you're at the point P, which is safely away, or if you're on a set, well, you have a function P and you consider the set where this norm is safely away from alpha. If you perturb a little bit, you want to make sure that you still stay away from the alpha. And this is why I need the L infinity topology, because that's also very often one of the complications. You only have LR regularity, R less than infinity, but you have constraints which are pointers almost everywhere, which are indications of L infinity type topologies. And this gap has to be somehow overcome. This is what we nevertheless have to do here. So you write down the Newton derivative. It looks complicated, but on the other hand, if you just go to the calculus, you'll see that this is just what you expect. If you differentiate the L2 norm at every point and you bring this in, and consider the fact that alpha is positive, you'll end up with this quantity on the so-called active set, which means where max is just this term inside here. And if it's if you're on the so-called inactive set, which is everything else, everybody else, then you can somehow specifically choose this derivative. I mean, this is just one selection. Remember, I gave you this theorem which says you can make a selection. So this is not an arbitrary element. This is a particular selection because I made a choice on the on the set where the max would be non-differentiable. Okay. But this is a valid Newton derivative.
So, when you do this in for H for a finite element approximation, is there any restrictions on the way? I mean, is it practical? Is the scheme practical?
You mean the mesh independence result?
Yeah.
I mean, for instance, for this mesh independence result, if we go through a simple example of controlling Poisson's equation by the right-hand side and doing, for instance, the usual P1 approximation, so like piecewise linear globally continuous elements, the whole theory just, so this is just perfectly suitable.
Okay.
So, for instance,
it's implementable.
It's implementable. If you do a semi-linear
without any branch integration, directly implementable.
Yeah. Okay, okay, so this would then be the corresponding Newton derivative. This is what you would use in this generalized linearization, and here you can already see how complicated this object could be, or the PDE could become if, for instance, you think that P is replaced by the gradient of some quantity, which sometimes it is, like in Bingham, then this would involve a kind of very nonlinear, complicated partial differential operator, which is also non-smooth and so on. Okay, in a specific case, if L plus M is 2, then you may just count dimensions and you will see that the P is scalar valued. And then, of course, if you have a norm or the absolute value less equal alpha, you get an upper bound and the lower bound, and you can write this thing as a max and min, and then the derivative simplifies. And taking the characteristic functions of these two sets is just one specific element of this derivative, of the Newton derivative. So the message is, in general, is L plus M is larger than 2, which means the P could be either vector or matrix valued. It's kind of complex, and this would be one specific element. If L plus M is 2, which means we have a scalar valued quantity, we have a lower and an upper and a lower bound, and one specific derivative is just the characteristic functions here of these sets where you violate the max. Well, the max is, the argument here is positive, and this one. So message, this is extremely simple to compute and reminds us a lot of this active-inactive set choice which we had in the method at the beginning. Okay, I think in a very abstract setting I've written down first order conditions, but maybe since it's late in the afternoon I don't go through all the details. So what you see here is just this operator which you got from the first order conditions of the dual problem, which are called now d gamma. Remember, this was this additional regularization which we may need or not depending on the regularity of the problem. This is our linear operator B, which was part of this non-smooth part of the energy. A star is the operator which is associated with this dual bilinear form. Remember, the F star at some point is a structural assumption. And then you can write down the first order condition to look like this. Okay, again, this is calculus work to be done, but this is now in a very abstract way the partial differential equation, if you wish, the nonlinear one you need to solve. Okay, And the way how it's done is again by Newton procedure. You start with some initial guess. So it's all now written in lambda only. You start with an initial guess. You find, well, okay, sorry, so this is here written in lambda, but then the step again brings in a delta p, but I think it doesn't really matter because you can go between two variables just by this relation here. You linearize in a generalized sense at the current lambda k or pk, you update and move on until you are happy. So you always solve generalized linearization of this complicated non-smooth nonlinear partial differential equation. And the theory then, which we can draw from the general result, says if you're sufficiently close to the solution lambda gamma, you have locally superlinear convergence, and there is a very quick fix, and I don't go into the details to even globalize that convergence. So there is a kind of line search procedure which allows you to say, well, I don't need to start sufficiently close, I can start anywhere. The line search takes care of the fact that I really converge, and once I get into neighborhood of fast convergence, I'm really fast, and the line search should turn off. Okay, so this can all be done. Okay, and then there is a special case, as I told you, whenever this operator here is already regular enough, you don't need extra regularization, everything is fine, forget about extra penalization, just do as we did for the optimal control problem. Okay, and this would be, for instance, the situation if this mapping here is a mapping from L2 to LR, R larger than 2, because then we have this norm gap, we have this differentiability property, and everything is fine. Okay, I will finish off with 3 examples. Example number 1, you can find it, for instance, in Glowinski's book, is what we call simplified friction. And it's this particular setup here where you have the space Y, which is all elements in H1, which have a zero order trace on one part of the gamma, which boundary gamma, which is gamma naught here. You have another gamma boundary, subset of the boundary gamma, which is gamma sub f. And this one is supposed to be the friction boundary, if you wish. You have a force F in L2, and tau naught, again, as I said, is the zero order trace operator from H1 to H1 half. And in this specific framework, you have, for the smooth part of the energy, you have this F being just the usual one, and the operator B is the trace now of the function Y onto this space gamma F. And here you see an example where S, this set, is not omega, but it's just one part of the boundary. And if you go through the calculus, you'll see that this is a good case. This falls into the special framework, no additional regularization is needed, everything is fine. You can also already work on that basis.
Yes. Where's the other part of the functional?
Well, I haven't displayed because the other part was more or less fixed. So we said it's alpha integral over S norm B
that's what you mean.
y to some d ds maybe. So that was fixed.
All right. So it's
I'm talking about the
L, kind of the L1 norm of the trace of the solution on gamma.
Yeah.
Gamma
Okay.
N.
Yes. Okay. Well, image restoration. I think I don't go into the details. We already discussed this for a while. It's a bit more tricky because you may see that I added a little regularization here. I could open up another talk by ignoring this regularization and just go for the PV space. But many things we discussed were here in Hilbert space. PV obviously is not the Hilbert space. It's even a non-reflexive Banach space, so we need to be careful with respect to dualization, but there's also a way to go. But I think this would require another point of view and would take me too much time. But you can go through this as well, adding in this little regularization. Let's assume beta is much, much smaller than alpha. Actually, on numerical, we usually set it to 0. You see the setup we had earlier. You are given image data like this one. Could be a bit blurry, like an unfocused lens of the camera. Let's assume you know the blurring, which would be the operator K. There's also a version of the problem where you don't know this, but this is much more complicated. You would like to track the data, but you also need to filter, which is this total variation. And since I have this additional regularity, I really have the usual distributional gradient here instead of this generalized total variation definition. Of course, we have a more regular space, which doesn't allow jumps, so which means edges are ruled out, but at the same time, if b is much smaller, beta is much smaller than alpha, we still see sort of sharp.
Could you still not work in L2?
Hmm?
Could you still not work in L?
Yeah, I could.
Take beta equals 0 and work in L2,
I
and just say your
yeah.
functional is infinity if it's.
Yes. Yes, this could be done. So I could have, I can ignore the PV in a sense, but I could enlarge the space, work in L2, say, well, whenever I'm in L2, only not in PV, this term is just infinity, otherwise it's just what it is, total variation, and then dualize that one. Could be done, yes, I agree. And then it brings me back to Hilbert space. I agree. Okay, and then you just see a typical example for indeed this little image here. But I chose it a zebra for the obvious reason because you have sharp contrast here, which would be like edges in images. And what you can see here are 12 iterations. We usually do very inexact solves of the linear system, sort of inexact semi-smooth Newton. Here you can see we do 2 to 3 conjugate gradient iterations per linear system, which you need to solve for Newton's equation. The line search step is always 1. We could throw it away right away, actually. This is the superlinear convergence check. You can see that the quotient nicely goes to 0, so which means we do see superlinear convergence. And forget about the rest. I think this is just a residual quantity, and this is the variation of pixels of the constraint. But I think these are the important quantities. This tells us there's little effort which goes into each iteration. This tells us there are not that many iterations, and this tells us that the convergence is superlinear. So this is what we should see. And we could even have a resolution-independent convergence now, which would mean if you have an image with a higher resolution, which means more pixels or finer discretization, you would see that the number of iterations doesn't really grow. Although, of course, the effort per iteration grows. And finally, for Bingham fluids are in some sense a bit more convenient than total variation if you wish up front, because you have here in the F the usual Dirichlet type energy with this force F acting in Y star. The B is now the Nabla operator, similar to what we see in total variation regularization, with this additional beta term. Otherwise, of course, we would need to be a bit more careful. And then you can set up the dual problem, and you indeed get the format as we have seen it before. And here we see the adjoint of the B operator, the negative adjoint, I should say, of the B operator, which is the divergence operator. And again, this problem fits into this theory. It's a bit more complicated because of the setup here that we also need to have the solution operator of the Stokes problem, which comes through the dualization process into the game here. But otherwise, you can solve the Bingham problem by looking at the dual and go through this framework, and then you would have a mesh-independent algorithm. And here's just one example, but I think you might have seen such pictures already before. And here we can again see the superlinear convergence check, so which means the quotient goes to 0 as the iteration moves on until we have 23. Okay, this brings me to the end. Let's see. I'm still six minutes ahead of time, which is a miracle, I must say. Of course, I don't tell you that.
Possibly comment.
But of course, I don't tell you that.
Yeah.
Of course, I don't tell you that I prepared another 40 slides, of course.
No, don't tell us.
Okay, so I think I more or less gave you a summary already, but let's just quickly go through this because there was lots of material. There are many ways to solve variational inequalities. I gave you one particular angle, as I explained to you, using this Moroyoshida-based path following. So we use it whenever we don't get Newton-type theory right away, but we need to regularize in order to get function space methods. Path following is reminds us of the fact that we at some point have a parameter which we need to update, and we need to understand how all the quantities depend on this parameter, and ultimately we use the value functional of the underlying minimization problem as our guideline for updating. So the value functional and its sensitivity as a guideline to update this parameter gamma. Remember, sometimes we have a very sharp curvature. We have to be careful with the gamma update. At some point, we hit the sort of asymptotic behavior, and then we can be very optimistic with the update, and there were specific rules to do so. For each fixed parameter gamma, we have this semi-smooth Newton method in function space, which also has a mesh-independent convergence behavior. I have not really talked much about adaptive finite elements. I just show you one little test case with the Kahn-Hillier connection with the Kahn-Hillier problem, where we used adaptive finite elements. There would be another story to tell. I'll just be very short on this here and say, well, what I don't do usually is I study the variational inequality problem, derive an error estimator for this problem, and then solve the problem and update according to the error estimator. Because as we have seen, maybe for the problem as such, we don't have a mesh-independent solver. So I somehow study RFEM for the Moreau-Yoshida regularized problem, and in that way intertwine the adaptive cycle with the Moreau-Yoshida path following cycle and get the sort of overall convergent method. Okay. We have seen obstacle problem, phase separation, other examples. For variational inequalities of the second kind, and remember the difference is here the non-smoothness is an indicator function, here it's just a proper convex function. It sometimes pays to look into Frenkel duality because it transforms the more complex problem into a problem which looks like a problem of the first class here. You may need to do a dual regularization, perhaps in addition to Moreau-Yoshida, in case you don't get this norm gap which you need for generalized differentiability, but there are many examples where you have it naturally. And again, the advice is whenever you can analyze the problem without additional regularization, just do it as we did for the PD constraint optimization problem. Use semi-Newton right away. 3 examples: simplified friction, image restoration, Bingham, but of course there are many other contact problems and so on. And as we've seen also many optimal control problems with constraints on the state, its derivative, which would be gradient type constraints, and or constraints on the control can be also formulated as variational inequalities of the first or possibly second kind. And again, this would be a solver framework for such problems. I have not touched quasi-variational inequality. We also worked on quasi-variational inequalities where the constraint set depends on the solution in its own right, and the quasi-variational inequality may not arise as a first-order condition of a minimization problem. So this is more often the case than it is a first-order condition of a minimization problem. But still, it turns out you can use a sort of fixed point iteration plus Moreau-Yoshida-based path following in order to solve also quasi-variational inequalities. And we did so, for instance, for the P-Laplacian involving gradient constraints. And this was for the elliptic case, for the parabolic case, and we also now look at hyperbolic problems, but this is kind of very fresh work. With this, I would like to indeed thank you very much for your attention throughout these 2 sessions. If there are any questions, I'm happy to take those, of course, either now or later today or tomorrow or whenever. And lots of, actually everything I've reported here can be underpinned by papers. If somebody's interested in getting the papers, just let me know. I can either send it right away or send hard copies. Thank you very much.
Thank you.